We're going to be talking about Chinese Postman Algorithm. And so first of all, we're going to discuss the differences in graphs, the difference between Eulerian, semi-Eulerian and non-Eulerian graphs, and what we can do with each. And then we're going to look at how we can use the algorithm to find an optimal route. So first of all, let's discuss the different types of graph: Eulerian, semi-Eulerian and non-Eulerian. So here I've got three networks, all slightly different, and we've got the nodes and the edges there. And what we're going to do is we're going to see if we can find a way through the network so that we travel over every edge just once and get back to where we started. So in this first network here, I'm going to try and start at A, and then I'm going to see if I can move from A and go over every edge just once and get back to where I started. And you can see that I can quite easily do that. And I can also maybe start at C, go C to E, E to D, D to C, and C to A to B, and B to C, and I can do that. So this network, it's capable to travel over every edge just once and get back to where I started. And we call this type of graph Eulerian. So this graph here on the left is called an Eulerian network, or an Eulerian graph. And it's named after a very famous mathematician called Leonhard Euler. And he was the guy who started graph theory with a problem similar to the ones we're doing with the Chinese Postman Algorithm, a famous problem called the 7 bridges of Königsberg. And I'm not going to go through the problem now. It's quite simple to understand, and you can look into that yourself. But when he looked at how to solve the problem, or whether it could be solved, he developed this this theory of graphs that we're going to be using now. So Eulerian graph is a graph where we can travel over every edge once and get back to where we started. So I'm going to write that down as a definition. We can start from one node, or start from any node, travel over each edge just once, and then return to the starting node. Okay, so that graph on the left is an Eulerian graph. So we're going to have a look at this next one now, and we're going to see if we can do the same thing. So I'm going to start at E, and we'll go E to D, D to C, and then we'll go C to A, and then we've got a problem because I can only go A to D now, and if I'm at D I have to go over an edge again. So let's see if I can do this another way. This time we're going to start at C, and I'm going to try and go C to D, D to E, I can go E to C, C to A, and again I get a little bit unstuck. So I'm going to try a third time, and this time I'm going to start at D, and I'm going to go D to A to C, C to E, E to D, D to C, and C to B, and that time I've managed it. And now this type of graph is called a semi-Eulerian graph. Because it seems that we can find a way through the network that only goes over every edge just once, but it seems to depend where we start. And we also didn't finish where we started. That's the other thing. On the graph above, we started at A, went around the whole network just once, and got back to A. Here I've managed to go over every edge, but I didn't finish where I started. Now, there's another way to look at whether a graph's Eulerian or a semi-Eulerian, and that's to examine the order on the nodes. And the order is how many edges go in and out of each node. So if we go back to this first graph, I can see that at A has an order of 2 because there's 2 edges in. B has an order of 2. C has an order of 4. D has an order of 2, and E has an order of 2. And if we look at this network now, let's just get rid of these bits here. If we look at this network, I see that A has an order of 2, E has an order of 2, C has an order of 4, D has an order of 3, and B has an order of 1. Now, this top one, this Eulerian graph, is Eulerian because every node has an even order. So that's probably a better way of defining it. Every node has an even order. Okay, let me underline that. And that means, or because of that, that I can start at anywhere in the Eulerian graph, go over every edge and just get back to where I started. Because having an even order at each node means that there is a path into the node and a path out of the node. For each node there's a path in and there's a path out. There's a path in and there's a path out. And if there's a path in and out of every node, if they're all even, then I can go into every node and come out of every node and get around the whole network and only go over every edge just once and get back to where I started. Now, in this second network, this semi-Eulerian network, all the nodes are even apart from 2. And when I tried to go around the network, I found that I couldn't do it if I started at certain places, but I could do it if I started from one of the odd nodes. Let's do it again. I go up here, down here, this way, this way, this way, and this way. Okay. So, semi-Eulerian graph is a graph or a network with 2 and only 2 and only 2 odd vertices. Okay. And it's impossible to start at a node and go over every edge and get back to where I started, but I can start at one odd node. I can travel over every edge and finish at the other odd node. And this is because, underline that's the most important bit really, a graph with 2 and only 2 odd vertices. This is because I'm allowed to do this with just 2 odd nodes, because as long as I start at one odd and finish at the other, if I start at B, for example, there's a path leaving B, but I never actually have to go back to B. So I only need a path that leaves B. And then if I go around the network, go over every edge just once, and come back to D, D's an odd number there, it's got an odd order there, but I don't have to leave D again, I only have to get there, okay, finally. So as long as I start at one odd and finish at the other odd, I can travel over every edge just once and get back to where I started. And that's called a semi-Eulerian graph. Finally, we come to this graph here, and let's just mark the orders on straight away. I've got an order of 3, 3, 4, 3, and 3. And it turns out, in this situation, if I try and go around the network in the same fashion as the other examples, it doesn't matter how I try it, I'll always come unstuck. And this graph is called a non-Eulerian graph. And it basically means I can't go around the network only travelling over every edge just once, no matter where I start. And we can define it by saying it's got more than 2 odd vertices. Okay, so what we're going to do now is we're going to do some examples of some questions and how we use those definitions there to help us answer or find the best routes through the networks. So here I've got example 1, okay, and I've got some nodes here, and the yellow numbers are the edges. They could be the distances or the times it takes to get around or something like that. And usually with these sorts of questions, it tells you the total. So if I add up 3, add 2, add 6, add 2, add 7, I should get 35. Okay. So what we're going to do is we're going to try and see if I can start at B. So this is going to be the question. Can I start at B and finish at B and travel over every edge just once? Well, first of all, the best way to find out if I can do it on that is check if it's an Eulerian graph. So let's put on the orders. There's an order of 1 here. There's an order of 2 at F. There's an order of 4 here. There's an order of 3 here. 2, 4, and that's it. So I've got 2 odd nodes. So let's just make a note of this. The graph then, this graph is semi-Eulerian. The graph is semi-Eulerian, which means that I can't start at a certain node, go over every edge and get back to where I started, because they're not all even. It does mean I could start at A, travel around the network and finish at C, because they're only 2 odd nodes, so I could do that. But the question is asking, can I start and finish at B? No, I can't. Not travelling over every edge just once. So if that's what it wants me to do, start and finish at B, then there are going to have to be some edges that I travel twice. And if there are edges that I have to travel twice, it would be a good idea to make these edges as small as possible, so my total distance is as small as possible. So what we're going to do is we're going to try and make this graph Eulerian by adding on the edges we're going to repeat. And we do this by pairing up the odd vertices. Because if I pair up the odd vertices, then the graph will become Eulerian. And then we can start at anywhere we want and get back there and only travel each edge once. So the first thing we always do with these questions is identify the odd vertices. Okay, so first step, identify the odd vertices. And then we've already done this. In this case, it's A and C. So you usually get a mark for just identifying the vertices that are odd. And what we're going to do is we're going to try and find the best way to pair up A and C. And the best way to do that is adding an edge here. I'm not really adding an edge, I'm just saying I'm going to do this edge again. And then adding an edge here, which gives me a total of 9. A to B to C is 9. Okay. So identify the odd vertices A to C, and A to C is a total distance of 9. Now I've added those edges, you can see that the network is now Eulerian, because this is now 4, and this over here is now 2. They're all odd, so I can start anywhere I want and get back to where I started. And the total route, or the optimal route, will be me travelling over every edge, which is 35, and then I'm going to add on the bit I've done again, which is just 9. So the optimal route is 35 every edge plus 9, plus the bit I've had to do again to make it Eulerian. Okay, so that's going to be, can't add 35 add 9 is 44. Okay. And that's usually what you're asked to do. I'm going to just add and ask another question now that you sometimes get asked, which is this. Let's suppose there's something at each node. These are different parts of the town, for example, and at each node there is a statue. So there's a statue here, 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 here and here. And I want to know, if I start at B, how many times do I stand next to a statue in my path? Okay. So, if I start at B, I stood next to a statue at the start, so I'm going to mark 1. I've stood next to a statue once at B. I'm going to travel B to C. I'm going to stand next to a statue there. I then travel C to back to B. And I stood next to a statue again here. Then let's go B to C there. B to F, and I'm stand next to a statue there. And then I go F to E, and there's a statue there I stand next to. And then let's go up here, and again I'm stood next to the one at B. And then I'm going to go B to A, stand next to the statue here. And then I'm going to go A to D, and stand next to the statue there. I'll go D to E, and I stand next to that one again. And then I'm going E to A, that one gets stood next to. And then finally A, back to B, and I stand next to this one again. So let's have a look at how many times I stood next to a statue at C, for example. I stood next to a statue at C, but you can see there's a link between the order of the node and how many times I go to the node. The order of the node was 2, and I went to the node once. So the amount of times I go to each node is half of the order. Okay, so you can see the order's 2, so there's a path in and there's a path out, which means I must have gone to C just once. Okay, and at F the order's 2, I went there just once. And at E, the order's 2, I went there 4 times, so it's half. You half the order and it tells you how many times you went there, except for where you started. Okay, where you started, the order here was 6. The order here is now 6. And I ended up going there 4 times. So I halved it and added 1. And that's because I started there, so I was already stood next to a statue there. Okay, so let me just make a note of this, and this is an important thing to remember. Okay, and that's this. Each node is visited n divided by 2 times. And that's where n is the order of the node. So if you want to know how many times you went to a node, you just look at the order and half it. Except the node where you started. How many times does this get visited? This gets visited. This is visited. N divided by 2 times, and then we add on 1, because it's where you started, you already stood there. Okay? So that's another sort of question you could get asked after you found your route. How many times do you go to, how many times do you visit node D or something like that? Okay, so what we're going to do on this one, slightly harder example, and we'll see why in a second. I'm going to give you the question, start at F, can we start at F and travel over every edge and finish at F? Okay, so the first thing we're going to do is we're going to identify what type of graph it is, can we do it or not. So the first thing I'm going to do is look at the order There's an order of 3 here, 2, 2, 3, 3, and 3. So this type of graph is non-Eulerian, which means that it's not going to be possible for me, as it is, to start at F and finish at F. So what we're going to do is exactly the same in the previous example. We're going to pair up the odd vertices, and we're going to add in the edges that we're going to do more than once, because we want to add on the edges we do more than once but make them as small as possible. So the first thing to do, like in the previous question, is identify the odd vertices. And the odd vertices here are A, B, C and F. But unlike the previous question, there's different ways I could pair these up. Okay, so let's have a look. I have different options. I could have A to B and C to F. I could pair those up. So A to B would be 4. I have to make sure that I write down the smallest distance between A and B. A to B is 4, and C to F is just 5. And that gives me a total of 9. Or I could have paired up A to C and B to F. That's a different way I could have paired it up. And the shortest distance from A to C is, let's have a look, 4 add 9 is going to be 13. It's going to be 10. A to F to C is 10, or A to B to F to C is 10. And B to F is just going to be 1, so that's a total of 11. And there's one more way I could have paired these things up, which is A to F and B to C and A to F. The quickest distance from A to F is 5, and B to C, the shortest distance from B to C, is not 9 but 1 add 5, which is 6, and that gives me 11 again. So once I've found all the different ways of pairing up the odd vertices, I pick the one that's got the smallest number, because if I've got to repeat the edges, I want to repeat the smallest ones. So the best pairing, the optimal pairing, is this one, because the other two are bigger. And so I'm going to add these edges on now. A to B, I'm going to add another A to B on, and C to F, I'm going to add another C to F on. And that makes the whole graph Eulerian. And then the optimal route is going to be the total of all the edges. So let's just add those up. I've got 9 add 1 is 10, 5 add 5 is 20, 3 add 7 is 30, and 6 add 4 is 40. So all the edges add up to 40, but then I'm repeating A to B and C to F, so I'm going to add on 9, so the optimal route is 49. Okay. And I could ask a question, how many times do I visit E? I visit E once, because the order there is 2. How many times do I visit A? I visit A twice, because the order there is 4 and a half. How many times do I visit F? I visit F 3 times, because the order there is 4, and I halve it and add 1, because it's a place where I started.
I didn't know that.
Now we're going to look at how to find the number of different combinations there are of pairing up the odd vertices. Now, if I've just got 2 odd vertices to pair, A and B, then I can just pair A with B, so there's just one combination. If I've got 4 odd vertices, A, B, C and D, then I can pair A with B, A with C, A with D. So there's 3 different ways I could pair up A with B, A with C, A with D. And that means that there's, and then I can just pair up the other 2 nodes, C and D, in one way, B and D in one way, and B and C in one way. So there's 3 different ways I could pair up A, and then that just leaves 2 nodes left, so there's one way I could pair up those. So there's 3 different ways I could pair up A, and then I'm left with 2 nodes, and I already know how many different ways there are of pairing up 2 nodes. There's just 1, so there's 3 different ways of pairing up A, and then for each way there's one way of pairing up the extra two. Okay. Now, on your questions, you probably won't be asked to pair up more than 4 odd vertices, but you might be asked how many different combinations there are for more than 4 odd vertices. So let's have a look at 6 odd vertices. A, B, C, D, E and F. Well, there's 5 different ways of pairing up A. I could do A with B, A with C, A with D, A with E and A with F. And for each way I pair up A, there are 4 odd vertices left. But again, I already know how many different ways there are of pairing up these 4 odd vertices, because I've done it over here. There's 3. So there's 3 combinations when I pair up A and B. There's 3 ways of pairing up the rest. There's 3 here, there's 3 here, there's 3 here, and there's 3 for this one. 1, 2, 3, 4, 5 times 3 times 1 combination. Which gives me 15. Now if there were 8 odd vertices, there would be 7 ways of pairing up A, leaving me with 6 odd vertices to pair up. I already know how to pair up 6 odd vertices. It's 5 times 3 times 1. So it would be 7 lots of that. 7 times 5 times 3 times 1. In general, if I have n odd vertices and I want to pair them up, n is always an even number so that I can pair them up, then I will get n minus 1 multiplied by n minus 3 multiplied by n minus 5 times, keep going until I get down to 5 times 3 times 1. That's the number of combinations. Different ways I could pair them up, but different combinations to check. And in general, what this means is, if I've got n odd vertices, say 10, I just multiply all the odd numbers below 10. So 9 times 7 times 5 times 3 times 1. And that's how many combinations there will be. So if I've got 20 odd vertices, it's going to be 19 times 17 times 15 and so on. And that's how many combinations you would have to check. Now, like I said, in your actual exam, you're either going to have 2 odd vertices, in which case there's 1 combination to check, or usually 4. Any more than 4 is going to get time consuming when you've got, for example, for 6 odd vertices, you'll have 15 combinations to check, which takes a lot of time, which is why they don't give it to you in an exam. But it might ask you how many combinations there are, and that's just a quick way of doing it. Multiply all the odd numbers below how many odd vertices you have.